Good afternoon, good evening, good morning, everyone. I'm Tony Yu, currently a staff scientist at the University of Chicago. So for this session, we have three LVP, really large volume press related talks, and two synchrotron future talks. So the first three talks are 30 minutes each, excuse me. A 1 minute warning will be given out 6 minutes before the talk ends, and for the 20-minute talks, it will be 4 minutes before the talk ends. So, for that, I welcome the first speaker, Donald Weidner from Stony Brook University. He'll be talking about the COMPRES LVP program. So, the stage is yours, Don.
Thank you. Thank you for the invitation. And today I want to summarize sort of things that are going on at the multi-anvil facilities that are supported by COMPRES. It happens to be at this time that there are really two places where work is going on, some at NSLS 2 and some at the APS. This generated from a single lab back in the time when before the upgrade of the NSLS, and we were at the NSLS, and when NSLS 2 was built, we realized that we needed to expand in some way to capture more beam time, as the initial NSLS 2 was going to be fairly light on operating beam lines. And so we now have operation at 6 BMB at APS and a second operation at the max PD at NSLS2. This is the XPD beam line. They share some things in common, and there are some differences between them. The APS system is a white beam. We do energy dispersive analysis. The NSLS2 is a monochromatic beam. So we do angle dispersive diffraction. In both systems, we have a large volume high pressure system that is complete with a uniaxial capability. So these both can produce at high pressure and high temperature. One can superimpose on the system a differential stress. But there is a different design. The one at APS is a D-dia, going back to the early days when we brought that into existence. And the one at the NSLS2 is, for us, a newer system, but it's based on the Kauai geometry of 6/8 anvils, and with the 111 axis vertical, and the top and the bottom rams move in on the sample to generate differential stress, as the 6 other rams are maintaining the hydrostatic pressure. With the APS system having energy dispersive, we built a detector, a conical slit, we call it, which allows us to have multiple detections all at the same 2 theta angle, but around the point of the detector. And the system, on the other hand, has a 200-ton press and fairly limited in pressure. The Kauai system has a 1,000-ton press, and so given higher pressures, but with the white beam and a 2D detector, everything in the beam contributes to the diffraction. Looking back on time, we can sort of say that the feature themes that come through most of the studies, or a lot of the studies, is a combination of stress, strain, and time, and how all of these features interrelate. These are players at the beam that are highly dedicated to it. Matt Whitaker on the left, the beam line scientist at NSLS2. Haiyan Chen on the right is at APS. Ken Baldwin and Bill Hipsch are support technical people. And then that's an old picture of me when I was an old man in the middle. Okay, so moving to APS, just a brief reconstruction is on the upper left, you see a picture of the D-dia, a cartoon of the D-dia on the lower left. This is the pressure generating system. The upper and lower rams are on have separate hydraulic systems to them to allow the differential stress to be added. We take images of the sample. This allows us to measure strain and so forth of the sample during the experiment of the entire sample. This is a picture of the conical slit system, and around a cone there are two circular slits, and we have an array of detectors around the cone that each detector simultaneously creates a diffraction pattern as the X-rays are on. If you think in terms of monochromatic light, these would be like different slices of the cake when you cake the beam going around in the horizontal direction. So this provides input to the stress field and so forth. And each detector has a diffraction pattern. And we have added to the system an ultrasonic collection system. This is fairly straightforward. It takes about a second to collect the data set, and it can be interfaced directly into all the software so that it can be triggered by the run computer in the system. Looking at it up close, this is what the sample looks like, the machine looks like. Putting the sample in, here are 4 anvils around the side. Top view after an experiment. This is the cubic system. At the NSLS 2, we use this a Kauai style system. We have put 8 anvils in, a carbide or centered diamond. We use 25 millimeters in the system. Here's a cutaway of such a system showing the internal jacks that push on the individual anvils, and the rest is pretty straightforward. And pictures in the lab of the DT25, which is our this guide block, this red guide block in the middle of the 1,000-ton press. There's me in the background for scale. You see it's a big press, and yeah, we have a conical hole so that we can capture light out to, I don't know, about 10 or 15 degrees. Also being used at our beamline is a system by the Corrado group, rotational Drickemer apparatus. This system is a uniaxial or a vertical press axis in a Drickemer style configuration of the cell, and the top anvil rotates relative to the bottom anvil, and it creates a pure shear stress on a sample at high pressure with a molybdenum foil here, allowing you to calculate the strain as the experiment continues. This group has been successful in doing experiments on the flow of mantle rocks into, or mantle-like compositions into the lower mantle, and that they've looked at a perovskite MgO combination. And I think this is probably a real breakthrough for beginning to get to flow properties of the lower mantle rock. Things that are really important to know in order to sort of calibrate the dynamics of the Earth's lower mantle. Well, another picture of our conical, this is the conical slit system. And this is an experiment, a deformation experiment where courtesy of Nat Dixon, and it's from Bill Durham's group, olivine under compression, the uniaxial stress is being loaded and then it moves, the stress field moves horizontally. We concluded about a 10 MPa accuracy in the system. One thing that very early surprised us was that each diffraction line defines a different stress level. Now that shouldn't have surprised us because the anisotropic properties of deformation of the plasticity are usually much greater than the elastic anisotropy in the system. And so what you begin to see is that different orientations of the different grains, which are the one thing that all of the grains that contribute to any one of these peaks have in common is the orientation of the grain that's responsible for providing diffraction. And so indeed, what may seem like a simple polycrystalline material, when it's compressed under differential stress, has a very heterogeneous stress field in it. And depending on the anisotropy, is the magnitude of that stress field. And so measurement of strain, we do sort of simple things. We put a metal foil in the sample stack. And so you can have 3 samples stacked on top of each other or more or less. And you just take pictures and measure the length of this as it evolves. You can use top and bottom samples that are some standard you have, like corundum, and the middle one being the sample. So you can compare the strain fields of the sample and of the reference. This is very convenient because of speed. It takes us maybe a couple milliseconds to get an image. If we wanted to do stress field with diffraction, that would take us 30 seconds maybe with the beam at the bending magnet at APS to get a robust measure of the stress field in the sample. So if you use simply the images and use this as a stress proxy, you can do real time-lapse experiments. You can do millisecond kind of exposures and watch the stress field evolve and so forth. One thing that we learned also fairly early is that our hydraulic pumps that apply shear stress, we can, they were driven by stepping motors, and we can drive them forwards and backwards just as easily. And so what we realized is that we can put an oscillating stress field on the sample, and it can be of varying magnitude and varying timescales, and give us lots of information. And this, well, in particular, we can go to frequencies a little over 100 millihertz. That's pumping oil through all the lines and so forth. That's, I think, what limits our high frequency end. But so we can go to, if we look at period 10 seconds, maybe a little smaller than 10 seconds. And we've done experiments with low frequencies where the period is like 5 hours. That's been the smallest we've tried. This particular example, we're just looking at the images, and as in the previous slide, using corundum as a reference and MgO as the sample. And if you look at the red and the green, the ratio of the amplitudes of those should be related to the Young's modulus of the sample if we know the Young's modulus of the corundum. And as the ratio is large, more similar, that means the Young's modulus is more similar. They're more different, that means the Young's modulus is more different. We can quantify this if we say we know the Young's modulus of the reference. And you can see in these two images, one with 11 millihertz and one with 150 millihertz second, that the ratio of the amplitudes are different. And the conclusion of this is that the effective Young's modulus with a 100-second period is lower than that of the Young's modulus of MGO at 10 seconds period. So this kind of experiment we can use for looking at dispersion of elastic properties. And this is in the range where we have very low amplitude vibrations. The different measuring tools, we can define where the data is taken, embedded in the sinusoidal stress wave that we put into the sample. And this can be stress, it also can be pressure that we vary like this, but we can identify exactly the phase that we're going to collect the diffraction, collect the image, collect the ultrasonic signal, so that when we're analyzing all of this data at the end, we know all the phase relationships between the different parts of the signal. Now, here's an example where where we moved into the plastic region by going to higher amplitudes. This is 2,000 seconds between these tick marks. And so this tells you that the period of this wave is a little less than 2,000 seconds. And this is the stress that we measured, as indicated over here in GPa. So it's going plus or minus half a GPa. And then we measured the amplitude of some of the diffraction lines. And this is the 111 diffraction line of MGO. And we plot amplitude as fraction of the total amplitude. And we see that also is sinusoidal. Hence, we're having diffraction peaks grow under certain conditions and shrink under certain conditions. If you might notice that the amplitude is 90 degrees out of phase with the stress, and I would contend that that argues that the amplitude is driven by strain, because in this case, if we're in the plastic region, stress is in phase with the strain rate, and the strain rate's 90 degrees out of phase with the strain. So this would be the strain in the sample, and this is for 111 peak. If we look at other peaks, they're either in phase or out of phase with the 111 peak, showing that some phases grow when stress increases or strain increases. Some peaks shrink during that time. Using these sinusoidal variations, the Dobson group designed experiments where they looked at, put markers in the sample that was just a line going through the center, and sinusoidally heated it, and the heatings from the furnace on the outside, by looking at the phase relations at different positions along here, the length of the sample between the lines being a proxy for temperature, they concluded the thermal diffusivity. And here's some results for majorite at 15 GPa. And as a function of 1 over temperature. And here they move into radiative heat transfer. So that this actually gives them a fairly robust results. If we want to look at volume in the sample, we can take an image of, put a rhenium foil in this case around the sample, and put that into the volume picture. We went through some strange, this is the way we heated the sample. We wanted it to get used to a certain temperature by going up and down, and then take data from the end. We use camera. We take, but before we do this last step in temperature, we turn the camera on at 30 frames a second and take images. And from the images, we deduce the volume of the sample, which is indicated here. This is a corundum sample sitting next to the blue is a corundum sample. These are 3 different temperatures. There were more than this, but to make graphs simple, and they're just displaced to make them look separate. The higher one, hotter one, is above the solidus of this peridotite, and we see that the effective thermal expansion is tripled as we cross the solidus. There's this little funny curvature at the beginning, always in these. Whether you go up or down, it's shaped like this. And again, that's the thermal diffusivity controlling how fast the sample heats up. So we concluded, again, the sample heats in like 1.5 seconds, and that crossing the solidus significantly increases the thermal expansion. We decided to try the same thing for bulk modulus. In this case, we can't turn the pressure up and down in a step function like we do in heating. We could probably set the furnace in like a microsecond. We can change the current running through the furnace. And putting pressure, it takes longer time to go through the line. So we set up a system at 3 millihertz. And we did this experiment again, stepping the temperature up in time. These are steps in temperature, and at each step, and the sine pump ran continuously through the experiment without phase change for the whole thing. There's no new introduction of phase. So this is a sine wave. And these are the 2 components of strain that we measured through there. And final result was a bulk modulus that looks something like this. It's pretty constant. Now, if I were wanting to report bulk modulus, I'd be kind of embarrassed with this big error bar for what you can do compared to compression, but we were limiting this to a small stress perturbation. We were measuring pressure and volume change over a small perturbation. But at the melting point, at the solidus, when we hit the solidus, once again, the bulk modulus plummets. And so we built a model around that, which I don't want to go into here, but it's just a kind of experiment that one can do with this kind of a system. Now, in conclusion, really all I want to say is that I think the future is bright to continue to do new kinds of experiments and gain new information about the internal processes going on in the system, looking at time dependence and stress and strain. What I would have put in proposals for, I haven't gotten any money yet, have been to add 3D imaging of the sample of the kind that they have working at Soleil. And I'm also interested in expanding the program to lower pressures. I know this is a place where there's a lot of diamond salt work going on, and I do believe high pressure is very important, but there are a lot of things of importance in the stress strain time relationship in the critical zone and in the crustal region that I think the kinds of tools we've been working on can play a big role. That'll be all. Thanks.
Okay, thank you, Don. We do have one question from Sergey. Sergey, could you please unmute? Okay, there you go.
Hi, Don. It is very good to see you.
Thank you. Good to see you.
Don, I have two questions, in fact. So one is, what kind of information would you like to extract as the end product from your from your frequency-dependent measurements of a Young's modulus? Are
Well,
you
uh,
are you trying to get to this viscosity or of
it, my purpose in it, or part of the purpose in it is to look at situations where dispersion can be an important thing, and so the Young's modulus is just one of the elastic moduli that come into it. Really, shear modulus and bulk modulus are the two that are sort of important in a velocity of acoustic waves, because a lot of our measurements in the laboratory of elastic properties are at fairly high frequencies, megahertz, gigahertz, uh, whatever, other than static bulk moduli. And so being able to do measurements at lower frequency uh, becomes important in sort of addressing that question. Now, the looking at bulk modulus, I thought was really important because the shear modulus has relaxations often at high temperature that lots of things can contribute to them. And Ian Jackson's work on olivines and various other things that have very high melting points still have a lot of relaxation. And the shear modulus decreases quite a lot at high temperatures. So that would mask any kind of intrinsic properties going on. And looking at partial melting has been something I've been working on. So that's why I wanted to do the bulk modulus. But Young's modulus falls in that same kind of category, and it's accessible.
So my second question is, in this melting experiment, so this KLB1 composition, was it a rock actually, or was it a glass?
It was a rock, a crystalline rock.
Okay, thank you.
Yeah.
Any more questions or comments for Don? I have a quick question for Don. The diffraction pattern that you were collecting for 30 seconds, what detector was that you were
Well,
using?
that's our conic, our multi-element detector, basically.
Oh, okay. So that's a single element.
Well, it's 10 elements.
Right. I mean, so it's a germanium detector, basically.
Yeah, germanium detector.
Okay. Thank you.